last thing we learned was that, um, oh, where is it here? We did this, back further. Yeah, I did this whole timing. I took a latch, transparent high latch, and a transparent low latch, combined the signals going through them. We did this whole analysis and we realized, oh, if I look at two latches like this, it actually looks like a flip-flop. And this time we got a negative edge trigger flip-flop. And I said, yo, if you reverse this, you put the bubble at the front and you get rid of this bubble there, then you'll get a positive edge trigger flip-flop. Yeah. And that's the last thing we left off at. And that's what this is. Next slide. Some other common things that we do are enable D flip-flops. Enable D flip-flop. And enable D flip-flop, well, at least one way to make it, we're going to talk about others later on, but this is a common way, is to take a flip-flop, put a mux in front of it, feed the Q back on one side, put the input on the other side, and then you have this enable. So when this enable is 1, the input comes through, we're enabling the flip-flop to clock in new values. When enable is low, then it just feeds back and it stays in its known state. So it's a way of sort of freezing a flip-flop from that, updating its values. You'll notice this enable, somebody just asked me, is still synchronous, right? It's not going directly into the flip-flop, so it still needs the clock for this to enable to happen, right? Toggle flip-flop. Toggle flip-flops are like they toggle back and forth from 1 to 0 to 1 to 0. And you can make them either by feeding the Q back through an inverter to the D input, or you can have Q bar rate into the D input, one or the other. But it just toggles back and forth. And they're very useful in making counters. And you can combine this toggling with this enable to make a toggle flip-flop that has enable. And so often it's kind of represented like this. It's a T flip-flop toggle, and it has an enable signal that allows it to either toggle or freeze into its current state. So a toggle flip-flop would have like this inverter. So it's either toggling when it's enabled, or when it's, I guess it's the opposite here. The enable will go, this would be the 1 and this would be the 1 bar. So when it's enabled, it's toggling. When it's not enabled, oh, actually, this would just go to Q. Kind of looks like this, I guess. No input. It's either toggling or not toggling. So that's a toggle flip-flop. Shift registers, we kind of did this already. This is just some code representing a shift register. And you can shift left or right. Nothing new there. The last thing is this, what's called a linear feedback shift register, or sometimes you hear them called LFSR, is the acronym. If you take a shift register and you feed back, particularly with exclusive OR functionality, into some of the points into it, you can make a circuit that's sort of a pseudo-random sequence generator. So if you look at this circuit here where the X output of the last stage is fed back to the input, but also it's fed back and XORed with the output of the first stage, then if you look at the sequence, there's two sequences are possible. If you start up in 0, it'll stay in 0. But if you start up in one of these other states, it'll go through this sequence. And it's called pseudo-random because it's got a limited, number of possible states. But the bigger you make the shift register, the longer it takes to repeat the sequence. But it's kind of pseudo-random. And it's used in all kinds of circuits where you need kind of random delays or, pseudo-random functionality of things. A common thing you'll see is delays. Like, I want to push a button and I wait a random delay before something happens. You'll use something like an LFSR. So it's just kind of like a souped up version of a shift register with some feedback paths. Yeah, and that's the end of those notes. So now it is bonus time.
Oh, sir.
Yeah.
Just very quickly, is it possible to create a circuit that actually gives like a random series of numbers?
A totally random?
Yeah.
Yeah, not really in digital world, but in analog world, well, they try to do it. It's an interesting question because if you want to create a chip that's impervious to people to figure out what it does, you want to have it to have some kind of randomization into it, like totally random. So people go to like extremes trying to generate like a random noise from a circuit, like take a transistor that has some or like a random Gaussian white noise and use that noise to make it do things. But it turns out to be really hard to do because even if you have a little transistor inside of a chip, for instance, say you have other circuits doing stuff and they're changing the power supply, that power supply can affect your little random circuit and make it not totally random anymore. So it's a whole can of worms. How do you really make a really random signal inside of a chip? It's not easy to do. Somebody had a question, Prof. I did always at neg edge of D in D, and I did not get an error. Rather opposite functionality. Same thing as doing it, I think, always at positive clock. And if you don't put the D bar, it'll let you simulate it, but it won't reset right. It's not resetting when the clock goes negative. That's the problem. Yeah. Okay. Yeah. I don't know if that answers your question, but yeah, digital circuits, it's hard to make it totally random. But you can have a sequence that takes a long time to repeat. If you make this like a 48-bit shift register, there's 2 to the 48 states in here minus 1. That takes a long time to repeat again. Yeah, so bonus time.